Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers. Brought to you by AGI Research Lab India, this podcast will focus primarily on program synthesis. I'll be your host, Brian Landers, and for our first episode, we're going to feature one of the world's leading program synthesis experts. Mark, please introduce yourself.
Thanks for the introduction, Brian. My name's Mark Santolucito, and I've been doing program synthesis research for about 10 years.
All right, I can't wait to dive in and hear more about your expertise because it is the topic of the podcast itself. I'm excited for folks to meet you. Today, we're going to talk about your paper, Grammar Filtering for Syntax-Guided Synthesis. Did I say that right?
Yes, indeed.
Amazing. All right, we're off to a good start. All right, so at a very high level, what is this paper about?
So the paper is at its core trying to combine two different approaches to program synthesis, one being more of a symbolic, formal methods-based reasoning approach, and the other being more of an intuition, machine learning-based approach. The approach we took was to put the machine learning in front of the formal methods-based program synthesis part of the pipeline. And so we're focusing on a particular type of program synthesis called syntax-guided synthesis. And the idea here is that you provide the syntax from which you can generate programs, and you'll search through this grammar, the syntax for a program that satisfies your constraints. In our case, we're looking at examples. Perhaps unsurprisingly, one of the main determinants of how long it takes to synthesize a program is how large your search space is. And how large your search space is in this context is defined by how large your grammar is. So of course, maybe the idea is let's see if we can prune that grammar, remove some elements of the grammar, shrink the search space, and speed up synthesis. Now the trick to this is that you have to be careful when you remove elements from the grammar, because if you remove the wrong element, then you can no longer find a solution. So how do you pick the elements to remove such that you speed up synthesis, but you don't shoot yourself in the foot?
This is amazing. Okay, this is exactly the kind of topic we want to focus on the podcast. So I'm really excited to chat with you about this. Every paper's got a story, right? How they came to be, what you were studying, who you were with, your co-authors. What is the story, the genesis behind this paper?
So this actually, I think, is the paper that has one of the best stories out of all the papers I've published.
Wow, cool.
The story goes back to a vacation I took to Bermuda. I wanted to go somewhere warm, but I didn't want to sit on a plane for too long, so I went to Google Maps and zoomed out and tried to find the closest place from New York.
Nice.
Turned out it was Bermuda. So I went to Bermuda with my wife, girlfriend at the time, and we were there for maybe a week or something. I don't remember, Christmas break, something like that. And we were at a cafe, and I saw in the newspaper there was a hackathon hosted by this guy, Jade, who I sent an email. I said, hey, I'm here. I do computer science. I was in my PhD at Yale at the time. And I said, can I join? And he shot me back an email. I was like, yes, absolutely. Would love to have you join. Maybe you can give a keynote. Or was it my wife that gave the keynote? I honestly don't remember, but we helped run the hackathon the next day. It was a great time. And at that hackathon, I met this student, Cairo Morton, who was a high school student at the time. And he was super into what I was talking about, was really interested in program synthesis. And he sent me some follow-up emails, talked to me after we got connected. Eventually, we ended up working on this problem together, and he even joined me at Yale for a summer. He got some funding from the government of Bermuda, so he was able to join. It was awesome. We spent the whole summer working together, as well as Elvin was also on this paper, who was also a high school student from Deerfield. And then it was my office mate, Bill Hallahan, and my advisor, Rushitsa. And so, yeah, we worked on this for a few months. I think it was December. I had met Cairo. We continued working. Then he joined for the summer. And then we wrapped up the paper sometime in September or so. I submitted to AAAI. And then actually AAAI was 2020, February or something. One of the very last conferences in person before the pandemic for quite a while.
That's right. Yeah. Yep. You just snuck in there. Is Cairo from Bermuda?
Yeah, he's originally from Bermuda. He just finished his undergrad at MIT, and now he's, I think, working for a machine learning startup. So very proud of how far he's gone.
Yeah, that's an incredible origin story of a paper. That seems pretty rare. By the way, was your wife really mad that you, on vacation, you found a way to
No, she
get
was
back to work?
She's also a professor of computer science, so she was in on it. My advisor always taught me never travel anywhere without giving a talk. So it was already the assumption there's no such thing as travel for fun. Everything is work. Work is fun.
This is amazing. All right, good advice. Maybe. So you kind of went into this. It sounds like Cairo picked up on something you were working on. Was that your work primarily to that point? Was this a topic that was very familiar to you?
So I was quite into the syntax-guided synthesis, program synthesis space. And at the time, it was like 2019, there was a growing interest in the neurosymbolic direction of program synthesis. And I thought, well, I didn't want to dive too deep, but I had this student who was super interested in the machine learning aspect. And it felt like this was a natural connection. I mean, in the end, all we had to do was build a classifier that says yes or no, should we include this grammar terminal in the search space? So from a machine learning perspective, it was something that I felt like, okay, I understand. We just have a simple neural net classifier, nothing too complicated. I can kind of handle this level of complexity because at the time it was all quite new to me. And so it was a kind of a natural fit.
That's amazing. All right. So it feels like this paper was just meant to be. And was it the hackathon that catalyzed the actual creation of the paper, or was that just the beginning of the collab?
I think it kind of was. I had been thinking about program synthesis for a while, but I think Cairo was just really on the ball and excited about this. I think I probably just said to him something like, I think this could work. Why don't you give it a try? And he gave it a try and got some good initial results, and we kind of took it from there. I mean, it took quite a while after this kind of initial push of looking at it and being like, well, that maybe there's something here, to really refining the idea and getting all the details ironed out.
Can you share, just for the audience, since we're going to be focusing on program synthesis in this podcast, what is program synthesis?
Yeah, so program synthesis generally is the idea from the world that I'm familiar with, is the idea that you have some formal specification and you want to automatically construct a program that meets that specification. I used to call it programming computers to program, which now feels very familiar, but at the time was kind of a wild idea. The specification the form that your specification can take can be in the form of examples. This is kind of the most familiar one, called programming by example, where you say maybe 2 maps to 4 and 3 maps to 6, and you can kind of understand what program I'm looking for. But you could have specifications in other formats as well. Natural language is one that we now call vibe coding.
I know it well.
Another specification format might be some sort of logic. So first order logic, saying I want a function that for every input, it takes 2 inputs, and the input should always be equal to one of the inputs, and whatever the output is, it should be greater or equal to both of the inputs, and this would be the maximum function. There's also temporal logic. That's actually something that I specialize in, is program synthesis from temporal logic, where we talk about how programs evolve over time. So it takes many different flavors, but at its core, the idea is automatically constructing programs with respect to some specification, whatever that may be.
This makes sense. And how does all of that relate to transformers, LLMs, which are sort of take most of the focus of our industry currently?
Yeah. It can take actually a lot of different forms, and this is kind of the exciting thing. Program synthesis is a very large problem, and transformers, LLMs, are a part of the solution to this very large problem. So in this paper that we're discussing now, one example is, well, we want to synthesize a program from a very specific grammar. Maybe I can shrink my search space, and you can use some kind of transformer, in this case a neural network, not really a transformer, but to shrink that space. You can also directly do the synthesis with a transformer as code generation from an LLM, for example. There are some challenges to that approach in that you never know exactly what you're going to get. You can't really control the code that's coming out, and it may be hard to interpret the code. So when you want to generate something that just kind of works approximately. This is a great solution. When you want to do more principled reasoning about a problem, you want to have a little bit more control over your space, and then you need to augment your transformer architecture with some more reasoning-based approaches.
That's really cool. Thank you. That's super, super helpful. What about syntax-guided program synthesis, or SyGuS?
Yes.
Was that a pretty well-covered territory when this paper was written? Where did that begin?
Yeah, so this paper was 2020, it was published, but most of the work was in 2019. In SyGuS, I think the first version of the syntax-guided synthesis specification format was released as a 2013, 2014, something like that. So as a problem area, I think it was well understood. Now, actually, SyGuS, the actual formalism, is just a particular specification format, but people have worked on the area of program synthesis for quite a long time. I think one of the earliest problems was the church synthesis problem. It was 1963, I want to say. So this SyGuS was just a formalization of one particular type of synthesis problem. At this point, people felt pretty comfortable with the formalization of the problem. There had been a number of SyGuS competitions, which compared different program synthesis engines to each other. I think the last one was in 2018, and then the pandemic happened. I don't know if anybody's picked it up since then.
What are those competitions like? I'm curious.
Oh yeah, it's kind of like sort of Olympics of program synthesis solvers. So there's a set of benchmarks that are in this SyGuS format, and there was a number of different tools that were sort of competing on this benchmark set. And so the benchmarks were split into different categories: programming by example, first order logic, bit vectors. So they have different focus areas, and then you could compare how each of these solvers do on the different problems.
Did this approach from the paper get to compete in any of these SyGuS comps?
No, I think the last SyGuS competition was 2018, so we missed that one. Part of the reason that the competition has not continued is because SyGuS does define a very narrow program synthesis problem. It defines a problem where you're given a grammar and you're giving a very formal specification and you want to find a program, which is very broad in some ways, but also it does have some restrictions. So for example, it doesn't have any notion of a weighted grammar. Maybe you prefer to use some functions over other functions. Actually may have this in the latest version, but there's many different variations on this type of problem. For example, like a temporal logic problem, or from natural language as another example, is something that people care about that isn't well encoded into SyGuS directly. So it's still very useful as a core tool, but it's not really the end-all be-all. And so people are building a lot of tools on top of SyGuS solvers to try and leverage this. I mean, this whole program synthesis space, there's many, many problems, and building real systems out of this requires piecing together all the latest research into some sort of coherent system.
That's really cool. I mean, I don't know about you, but I'm excited to explore this world and meet other superstars in this space, which will be future episodes. So stay tuned for that. I guess I want to ask, what is truly special about this paper? What were some of the new ideas that were introduced? And, before we talk about the results of what happened with those ideas.
Yeah. One of the things I was really excited about this paper was the way it combined the machine learning approach with the formal methods approach. There had been quite a bit of work in the neurosymbolic space around 2019, not quite a bit, but it was getting started, but it wasn't clear how we could combine the two approaches. And a lot of the work was focused on taking, for example, a SyGuS problem and trying to solve your actual program synthesis query with some sort of deep learning technique. And so what we did was instead say, we have very good tools for solving our actual synthesis query, but one thing they struggle with is the scalability. Can we use the deep learning to instead shrink the search space, but still use our formal tool? Now, the nice thing about this is you get a formal guarantee of correctness, you get a formal guarantee of completeness, meaning if a solution exists, you'll actually find it. So it just has a bit of a different space to the problem. Another very important example or property is that CVC4 at the time is what we used.
What is CVC for?
This is a SMT solver. It's a tool that's one way of solving SyGuS queries. And so that's actually what we were using. We were able to kind of black box the solver and say, okay, we're going to let the solver do whatever it does, which means we still benefit from any improvements made on the solver side. But because we're just focused on shrinking the search space, these are kind of modular with respect to each other. So it meant that you didn't have to tear out the guts of this SMT solver approach to program synthesis. You could still reuse that and reap all the benefits of an SMT solver, which is a feat of engineering in the world of formal methods and program synthesis. And we'd like to be able to leverage this, but we'd also like to have the deep learning. And we don't want to do some kind of deep surgery every time we want to make improvements to one or the other.
This makes sense. Okay, so I think we get a good picture of, the space you're playing in and, sort of the problem here in shrinking the search space. How precisely did you and Cairo go about doing that? Like, what is actually happening under the hood here?
Yeah, so there's two really important components that we needed to take into account. And this is something we discovered through the process. We knew we wanted to shrink the search space. So we said, okay, we're going to try and estimate how critical each grammar terminal to be to the solution. So what this means is if we have some function that maps integers to integers, do we think that plus is really important, or do we think that multiply is really important? Maybe both of them are important, maybe just one. And whichever ones are the most critical, we want to keep those because those might be required for a solution. So we need to first estimate the criticality. But now there's another aspect as well, which is if you think that something is not very critical, you think maybe I should remove it. But there's always a chance that you get this wrong. And if you get it wrong, then this can be really bad because if it wasn't critical, but it was helpful, then you're going to need to find a workaround. Or if it really was critical and you thought it wasn't, you'll never find a solution. So the other thing that we took into account was a timing estimate. We wanted to estimate how much time would we save if this grammar terminal was removed. If we didn't include plus in the grammar, how much time do we think we might be able to save for a problem that looks like this? That was sort of what we needed to piece together was, can we estimate the criticality? Can we estimate the time savings? And then we'll combine both of these estimates together to figure out which terminals we can safely and productively remove from the search space. And so actually, to do this, we had to create, of course, a number of examples to train our network on. The way we did this was by generating lots and lots of functions and then generating random inputs, semi-random inputs. They were structured a little bit. And then running these inputs through these random functions that we generated and collecting these input-output pairs. And then we were training the network for criticality on, given this input-output pair, what's the set of terminals that I needed in my solution? Now, of course, there could be many solutions for every set of input-output pairs. So this was just one guess. The whole thing is very heuristic-y, right? It's all deep learning. So we just need to get something that's approximately right. We did this for, I don't know, maybe like 15,000 functions or something.
Wow. Okay.
Just generated all of these. And then we also had to predict the timing. So took our input-output examples, ran synthesis, timed that, and then we timed multiple different versions of the problem. So we removed every terminal from the grammar and timed how long it took to find a solution, including if it timed out. And so then we were able to predict, given this input-output example, how much time would we save for each grammar terminal if we were to remove it from the set? And so in this way, we could maybe come up with some guess for which ones would be the most productive to remove.
All right, I'm dying to know what happened, but okay. So when you say functions, are these just mathematical algorithms, or what are these functions as, the inputs?
Yeah, these are functions similar to the way you'd think about a function in math. It's a function f of x that returns y. So it's also like a function that you might write in code. It's a little bit different because they're stateless functions. So there's no kind of global state, but that's it.
Okay. All right. So timing, removal of these terminals. What happened? Like, did number one, were you able to still solve the problem? And was it faster? How did it perform?
Yeah, so we were looking specifically at programming by example for strings. So we were looking over the space of string transformations. We ran this on the SyGuS benchmarks, and we put our tool in front of, we were using CVC5, so CVC4 at the time, as our SyGuS synthesis engine. And what we found is that for 50% of the benchmarks, overall, we saved 50% of the runtime. So it was a pretty huge increase. There were a number of problems also that were timing out without our tool that now came into scope. I think there was one or two where we unfortunately removed an item that was critical to the grammar, which obviously meant then you get timeouts on those. So we thought, wow, this is great. Maybe we should just put this into CVC4. And so we messaged Andy Reynolds, who's the guy who develops, one of the main developers, really the main developer of CVC4, now 5. And we said, hey, what do you think about this? And it was a very interesting conversation. He said he was very worried about completeness, right? And so, as I mentioned before, if you remove a terminal that was necessary for your solution, you won't find the solution. Now, if you don't do this, CVC4 has a very nice property, which is called completeness. And that means that if a solution exists, we'll eventually find it. Depending on the context and who you're talking to and when you're using program synthesis, this completeness property may be more or less important, but it's certainly a nice property to have by default, because once you lose that, it's very hard to recover that property. So this tool didn't make it into the default implementation of CVC4, but it still works very nicely as an attachment that can go in front of CVC4 or really any other SyGuS solver.
By the way, just to connect a couple dots, CVC4 was the 2019 SyGuS competition winning solution.
It was 2019.
So 2019, yes. But also just that was the sort of state of the art at the time.
Yeah, that was the state of the art, and we were able to improve upon that by about 50%.
So, 50% faster sounds like a pretty darn good result to me. Were you happy with the results? Was that a great finding?
Yeah, it was. We were really excited, published at AAAI, got some really good feedback. Actually, one thing I'd love to do is revisit this, because CVC5 now is much faster than it was in 2019 when we did this work. And I think the really interesting thing is we should, I think, maybe be able to use better machine learning models to predict the criticality of the grammar terminals. Now, that work, we were also only looking at string transformation. So it was the programming by example for strings track of the SyGuS competition. And there's a lot of other really interesting ones. The bit vector track is really cool. This one connects a lot to some low-level hardware stuff. So there's a lot of interest in that bit vector track for FPGAs and this kind of hardware programming. But we never got around to implementing it. We just didn't have time. We got up to the strings and there was a paper deadline. So I think it would be really interesting to look at how you could build on those results with the modern technology and trying to tackle a broader range of benchmarks.
That's a pretty cool result if a paper is still, relevant years later and the author wants to keep pulling the strings. I mean, that's like, I think, pretty successful.
I hope so.
Well, there's a lot to be discovered in program synthesis too. So I think even though it's not a new sort of area, it's still got a lot to be discovered and explored.
Absolutely. Yeah, I think program synthesis was starting to really, from a formal methods perspective, was really running up against a scalability issue around 2019, 2020 or so. And that's when this neurosymbolic approach started to get some legs. And, recently it's really been taking off. I think there's a lot of excitement that this idea of automatically constructing programs that are guaranteed to be correct with respect to your specification seems like a super cool thing. It's super hard to do from a pure reasoning perspective, but if there's some way to combine this with more of an intuition guidance, then a lot of things unlock.
Yeah, that sounds pretty promising to me. Okay, so, AAAI accepted the paper. Did you present it there as well?
Yeah, actually, this was something I didn't know. So in the AI community, apparently, if you get an oral presentation along with your paper, this is supposed to be a good thing. I didn't realize this, and actually the conference organizers emailed us and said, congrats, your paper is accepted, and you'll have an oral presentation. along with the poster. And then we were really confused.
So
we were like,
just the poster is the other option, just poster
yeah, just
only.
the poster is sort of the other option, and we don't have that. In the formal methods community, every paper that gets accepted gets presented. It's a much smaller community, and so it just functions a bit differently. So we were super confused. We were like, what are they saying? Was the paper really accepted or was it not? But we were able to give this presentation and it was pretty well received. And there's been quite a bit of follow-up work in this line, as we see now, of combining this kind of neural guidance with symbolic synthesis techniques.
That perfectly leads to the next question I have, which is who should be interested in this paper? Whose work is relevant here?
Yeah, I think anybody working in program synthesis in this neurosymbolic space where you're trying to combine automated reasoning techniques with more of this deep learning style guidance. This is a very simple technique that we employed of just classifying grammar terminals and trying to select for the best ones to remove to shrink our search space. But at a high level, this is probably a problem you're going to come across in quite a few different domains. So leveraging some of the existing solvers out there that take more of a formal reasoning approach, but then trying to shrink the space to make their job easier with some deep learning should be a pretty attractive direction.
That makes sense. All right, Mark, thank you for kicking off the Abstract Synthesis podcast.
Happy to be here.
And for everyone listening out there, we'd love to hear your feedback, your thoughts, what you'd like to hear more of or less of on this podcast as we move forward. But we look forward to seeing you all on the next episode of Abstract Synthesis.